Hi and welcome to John's Maths book. In this video we're going to be looking at finding the area of a circle with a section removed using double integration. If you like the video then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. We're given a uniform circular disk represented in Cartesian coordinates by x squared plus y squared minus 2ax equals 0, where a is a constant. We are told that the disk has a segment removed from it, making a cut along the line x equals b, where b is greater than or equal to a and less than or equal to 2a. We're then asked to formulate the remaining region D as a set of double integrals of x times dA. Let's now focus on the area of the disk where y is positive. We can then multiply the integrals by 2 as this area is reflected where y is negative. We need to consider the green and red shaded areas separately and formulate integrals for each. The diagram shows an angle theta which varies between 0 and 90 degrees. When the line x equals b cuts the disk, we see that theta equates to an angle alpha. If we focus on the green shaded area first, we see that as theta increases from 0 to alpha, the radial distance denoted by r will vary in length as it reaches the line x equals b. The length of each value of r can be calculated as each will make a 90-degree triangle with an included angle of theta, and we know that the adjacent side is of length b. So using SOA cat TOA, b divided by r is the adjacent side divided by the hypotenuse side, and it is equal to cos of the angle theta. So r is equal to b divided by cos theta. So our first integral will sum infinitesimally small sections in the r direction, starting at 0 and finishing at b divided by cos theta. When using polar coordinates, the region dA, as shown in green here, is denoted by r dr d theta. This represents an infinitesimally small width multiplied by an infinitesimally small length. Also, when using polar coordinates, x is given by r cos theta and y is given by r sin theta. Our second integral will be from theta equals 0 to theta equals alpha, as this covers the green shaded area, and it will sum all the infinitesimally small slices of area calculated from the first integral. We are integrating x times dA, which, as we've seen, equates to r cos theta, which is x, and r dr d theta, which is dA. Simplifying this, we are integrating cos theta multiplied by r squared dr d theta. And we must not forget to multiply this by 2, as the green shaded area is reflected below the x-axis. So now, focusing on the red shaded region, we need to find this area and add it to the green shaded area that we've already determined. To do this, we need to calculate the small slices of area where theta goes from alpha to 90 degrees or pi by 2. The first task will be to integrate or sum in the r direction from r is equal to 0 to where r meets the boundary of the disk. This will give us a small slice of area. The radial distance will vary in length determined by the circular disk. To determine our upper limit of integration in the r direction, we need to take the equation of the disk represented in Cartesian coordinates and convert to polar coordinates. To do this, we will substitute r cos theta for x and r sin theta for y. After making the substitution, we're left with r squared cos squared theta plus r squared sin squared theta minus 2ar cos theta equals 0. Simplifying this, we have r squared multiplied into the bracket of cos squared theta plus sin squared theta is equal to 2ar cos theta. And using the trig identity, cos squared theta plus sin squared theta is equal to 1, we're left with r squared equals 2ar times cos theta. And dividing both sides of the equation by r, we get r is equal to 2a times cos theta. So when integrating in the r direction, we are integrating from r equals 0 to r equals 2a cos theta. And once again, we're integrating x dA, which converts to cos theta r squared dr d theta in polar coordinates. Our second integral will be from theta equals alpha to theta equals pi by 2, as this covers the red shaded area and it will sum all the infinitesimally small slices of area from the first integral. As before, we need to multiply the double integral by 2 in order to capture the area shaded in red below the x-axis. Now we've defined the double integral, I'll evaluate it in part 2.